This week we're going to cover Chapter 7, which is the topic of K nearest neighbors in the Shmueli textbook. And if you have a chance to look at the recommended but not required reading in Lenoff and Berry, that's going to be Chapter 9. And you'll find a little bit deeper discussion about K nearest neighbors in that text. Some of the examples that are included in the Lenoff and Berry book are Shazam, where you can click on an audio file and have it identify the audio. Another example of K nearest neighbors is book recommendations or song recommendations in either Amazon or iTunes. So we can talk about K nearest neighbors first by looking at the characteristics. This is what we call a data-driven technique. We're going to do several of these in this course, and not a model-driven technique. And that means that we're not going to fit any models like we did last week with multiple regression. We're also not going to make any assumptions about the data. And we're going to have just a simple, straightforward method that we go through in order to determine the closest data points to the ones that we're interested in scoring. So think about Amazon. You get on there and you have a purchase history, and they keep track of the things that you've purchased, and they of course want to get you to buy more things, and so they're going to make recommendations, but they don't want to waste your time and they don't want to waste their time, so they want to make recommendations that are going to be highly probable that you're going to be interested in, even if you don't purchase them, if you look at them and maybe put them on a wish list or something like that. So they look at all the purchases you've made, and that tells them what kind of things you like. And they go out and look at everybody else who's purchased the same things, and then they say, well, what have other people purchased that you haven't purchased? And then they make a recommendation, assuming that you guys are similar. And so the idea here is to take P different variables and measure how close the record is that you want to score with every other record in the data set. And then you're going to classify the record according to whatever is the predominant class among the neighbors. And so the question is, first of all, how many neighbors should we be considering, and what do we mean by nearby? Well, nearby is usually determined by what we call Euclidean distance. This is the same Euclidean distance that you learned back in geometry in high school. The idea is to take your data value, x1, and subtract from that the first variable for the first data point, square that distance, do the same thing for all the other variables for that first data point, and then take the square root, and that gives you the Euclidean distance between you and the first point in the data set. And you're going to do that for all of the data points that you have, and then that will tell you which one you're closest to. Now there are lots of other distances or measures of distance that you can use, and some of them are in the textbook. There are others in the Lenoff-Berry book that are described, and this one is used most often because it's fairly simple computationally to calculate. So to further illustrate this, if we look at the riding lawnmower data, we have income on our x-axis, lot size on the y-axis, and then we have ownership of a riding lawnmower in red and non-ownership in blue. And we come up with a new data point. We have somebody come on our radar who makes $60,000 a year, has a 20,000 square foot house, and we want to know how likely they are to be an owner. Should we solicit them by sending them a mailing? And so we would look at that value, 60,000, 20,000, and say which one is the closest data point, and it turns out the closest one is number 4 right here, and so that is an owner. And if we were using just one nearest neighbor, we would say whichever one we're closest to, that's how we're going to classify. So if we're using k is equal to 1, this new household would be classified as an owner, and we would send them a mailing. And as we can see here, we have 2 out of the 3 nearest neighbors are owners. That would tell us then we're going to classify this new household also as an owner if k is equal to 3. And that brings up a good question then. How do we pick k? How do we And we're going to use the validation data set and look at the error rate on the validation data set. And that's going to be the basis for picking the value of k that we're going to go with. Turns out that there's a trade-off between picking a low and a high value of k. And this is the same bias variance trade-off that is in all of statistics. If k is low, there's going to be a lot of noise, and if k is high, there's going to be less noise, but the model is going to miss the local structure, in other words, not fit the data as well. If we let k equal n, in other words, all of the data is considered the neighborhood, then we have the same thing as what we referred to earlier in class as the naive rule, which again just says classify all records according to the majority class. Let's go back to our example with the riding mowers. We've got 24 households that either own or don't own riding mowers, and we want to use k nearest neighbors on income and lot size. And in order to do this, we're going to partition the data into a training and validation set, and we're going to do this with a 75-25 split. And you can see there's 18 households and 6 households in the training and validation sets respectively. So we're going to have our validation data that we're going to use to find the best value of k, and we're going to do this with k equals 18, and that represents the total number of records in the training data. Now this is a very small data set, and you would never do this sort of thing on a data set this small, so this is all just for illustrative purposes. And we can see that the best value of k appears to be 8, at least for this partition, and k equals 9, 10, and 12, and 14 also have the same rate. So if we look in the k nearest neighbors output and jump, we'll go down here and see here's the misclassification rate in the validation set, and we go down and we see that here at k equals 8 we have 1/6, and so we have one of those 6 that is misclassified, but we also have the same at 9, 10, 12, 14, and so all of those have the same misclassification rate, and so we will refer to Occam's razor, or the most parsimonious model, to determine that k equals 8 is actually the best of those, because it is the simplest and yet explains just as much of what's going on as the other models. How do we do this in JMP? Let's go over there and check it out. First of all, you're going to want to open up the riding mowers KNN data set. You'll see there's 24 observations, lot size, and the ownership. And we have the same validation set as that in the slides. And if you look at the riding mower without the k nearest neighbor, I believe you have a different validation set, or maybe not even a validation set. So from here, we want to go to Analyze, Modeling, and then Partition. Our Y variable is going to be ownership, so we can highlight that and click on Y. Lot size and income are going to be our X factors, and validation is going to be our validation set. The next thing we need to do, and this is very important, is select a method. Decision tree is the default. We will talk about those later in class, but for now we want to look at k nearest neighbors. When we say OK, this is going to ask for the maximum number of k, and we'll put 18 in here. Typically you're not going to do that because you don't want to do this for the entire training data set necessarily. So we would say OK, and here's the results that we get on the validation set, on the training set, and we can see this is what we're interested in. We look at k is equal to 8, and there we have 16%, or 1/6. Here it tells us we misclassified 1 out of 6. So let's look at this data one more time just to show you how sensitive k nearest neighbors can be to the validation data set. So we're going to go over here to Analyze, make that Columns, Modeling Utilities, Make Validation Column, and we're going to do another 75-25 split. We're going to call this Validation 2, and we're going to say do that purely randomly. and you can see that we have a different validation set. So now when we go over here to analyze, and then modeling partition, and we recall what we had before. So it's everything in, except for now we want validation 2 as our validation, which it looks like we have to remove the first one and then add in validation 2, k nearest neighbors. Okay, and let's put that back to 18. And how are the results different? Well, they are different. Well, it looks like we have not a 75-25 split. We got 19 over here and 5 over here. But you can see that the one with the best error rate is k equals 1. So 20% misclassification. There's a bunch with that, and 1 is the smallest. So when you have a small data set, that's typically what you can expect, and that's all based on the random seed. So if you want to duplicate what's done in the textbook, you've got to use this validation column. So let's go back to our slideshow, and what if we want to classify new records? We can do that using the predicted formula ownership, and we did this before, but we'll go ahead and do it again. So let's go back over to our data set, and we're going to need to get our model again, or actually not our model, but run this again and say OK. And then we need to save the predicted formulas. So we'll say save predicted formula. And it asks us how many we want to do this for, and we want 8. That's the number that we decided was the best value of k. So we're going to say OK, and now we're going to close this and come back over here, and it says predicted formula ownership 8. This is for this training data set, and we're going to do it again for validation 2. And so let's go back here, analyze, modeling, partition. Let's recall, get rid of that one, throw validation 2 in, say OK, and we'll go 18 again. And now we have this output, and we can save the prediction formula. And this one, remember, we said the count was equal to 1 was the best one, and so we're going to say 1. And so essentially what's going on is we have 2 different predictions, and we can see where they differ if we like. But if we want to add in new data, all we have to do is come in here and put in the values of the data. There's 60 and there's 20, and we can see that based on either the 8 nearest neighbors or the first nearest neighbor, both of these are going to predict that to be owners. So instead of using majority vote to determine the classes, another alternative is to use the average of the response values, and that's if you have, instead of a classification outcome, a numerical outcome that you're trying to do prediction. And in such cases, you can also have it be a weighted average, where those that are closest in the neighborhood have a higher weight, and the weight decreases with the distance. So this is something you can use with classification and prediction, and so that makes it a very useful tool for data mining in general. The advantages of doing this is it's very simple, and you don't have to make any assumptions about the normal distribution, etc. And you can effectively capture complex interactions among a lot of the variables without having to define a model, because again, this is a data-driven thing. Shortcomings are that as the number of predictor variables increases, the required size of the training set is going to increase exponentially, and this is because when you move into multiple higher dimensions, space gets spread out more and more and more, and that's problematic because you need a large training set, and the larger the training set, the longer it takes to find the distances to all the neighbors and identify those that are closest. And so this is what we call the curse of dimensionality, and you generally think of more data as being good and containing more information, that's true, but the more dimensions you have, the more complex things get and slower computers run, and that can be problematic. So how can we deal with this curse of dimensionality? Well, we talked about principal components a few weeks ago. We can use that or other techniques to reduce the dimensionality. There are oftentimes computational shortcuts, and in this setting you can get an almost nearest neighbors. For example, JMP doesn't make predictions or doesn't calculate all the predictions until you save the prediction formula in the data table, and that prevents all sorts of computations being done in order to save time. And once you pick the model that you want to go with, then you can save that, and predictions are made. So what we're doing here is just finding the distance between each record that we want to classify and all of the other records. We're going to select a neighborhood that has the k nearest records, and we're going to classify according to the majority vote if it's a classification, or if it's prediction, then we're going to take the average of the nearest neighbors. And due to the curse of dimensionality, oftentimes we're going to need to limit the number of predictors. Otherwise your computers are going to run all day long, and that's not good. So that's what I've got for this chapter. We will see you guys in the next video.